Please subscribe to support the channel. If I told you the trip to Jupiter can be anywhere from under a year to nearly a decade, that isn't clickbait. It's the honest headline number. Because the travel time isn't a fixed property of Jupiter. It's a direct consequence of how you go. A lightweight robotic probe can be launched on a higher energy, faster trajectory, often with trade-offs like less payload and a hotter, riskier arrival, while a more typical science mission accepts a longer cruise to save propellant, reduce launch demands, and improve reliability. And the moment you switch the question from robots to humans, the clock gets pulled in opposite directions. People need heavy life support, shielding, redundancy, and abort capability, which makes going fast harder. Yet long exposure to radiation, isolation, and microgravity makes going slow less acceptable. So how long to Jupiter is never one number. It's a scenario-based range shaped by fuel, rocket power, mission risk, payload mass, and whether getting there means a quick flyby or arriving slow enough to stay. That headline range only makes sense once you pin down what you're actually crossing, because Jupiter isn't a fixed X miles away destination on a static map. Earth and Jupiter are both orbiting the Sun, and they're doing it at different speeds. Earth completes a lap in 1 year, while Jupiter takes almost 12. So the separation between them is constantly changing, sometimes bringing them relatively close on the same side of the Sun, and sometimes putting them far apart with the Sun between them. In other words, the baseline distance isn't a single number. It's a moving target that depends on where both planets are on the day you leave and where Jupiter will be on the day you arrive. This is why you'll hear wildly different distance figures quoted for Earth to Jupiter, and all of them can be technically correct. At favorable alignments, the straight line separation can drop to only a few 100 million miles. At unfavorable alignments, it can approach around 1 billion miles. But even those numbers can mislead because spacecraft don't travel in a frozen snapshot of the solar system. They travel while the solar system continues to move. The route is planned so that the spacecraft intercepts Jupiter's future position, like throwing a football not to where the receiver is standing now, but to where they'll be when the ball arrives. And there's a second twist. The distance the spacecraft actually travels is usually longer than the as the crows fly separation at launch, because the vehicle is following an orbit around the Sun rather than drawing a straight line through space. Think of it less like driving across a flat field and more like merging onto a larger, faster highway lane. You're reshaping your solar orbit from Earth's neighborhood out toward Jupiter's, which naturally creates a curved path with its own length. That means two missions can both go to Jupiter, launched in different months or different years, and one can have a noticeably shorter path simply because the orbital geometry was kinder. So before we even touch engines, fuel, or fancy tricks, the stopwatch is already being influenced by celestial choreography. The distance to be covered expands and contracts with alignment, and the spacecraft has to time its departure to meet Jupiter where it will be later, not where it is now. That timing dependence leads directly into the next crucial idea, because if the distance is changing and the target is moving, you can't just leave whenever you feel like it, and you can't define going to Jupiter without defining what counts as arriving. And once you accept that the target is moving, the next trap in the question becomes obvious. Go to Jupiter can mean 3 very different things, and the definition you choose can change the mission time by years and change the energy requirements by an even bigger factor. In casual conversation, getting there sounds like one finish line, but in mission design, it's more like choosing between 3 finish lines with different rules: a quick pass, a committed stay, or a precision delivery to a smaller world that happens to live in Jupiter's neighborhood. A flyby is the simplest meaning of go to Jupiter, and it's the reason you sometimes hear relatively short travel times. In a flyby, the spacecraft's goal is to arrive at Jupiter's vicinity on a trajectory that swings past the planet, gathers data for hours to days, and then continues onward, either into a new solar orbit or toward another target. Because it does not need to stop, it can tolerate arriving at very high speed. That matters because slowing down in space is expensive. If you're willing to come in hot and keep going, you can prioritize a faster cruise and higher arrival velocity. The trade-off is that your prime science window is short, your observation geometry is constrained by that brief encounter, and you get only what you can collect as Jupiter races past your instruments. For some objectives, first reconnaissance, broad measurements, a gravity assist to somewhere else, this is a perfectly rational choice. Entering orbit around Jupiter is a different category entirely, because now arriving means you must reduce your speed relative to Jupiter enough that the planet's gravity can capture you into a bound orbit. This is the braking problem in its earliest form, and it can dominate the mission architecture. When you come in from interplanetary space, you are carrying the kinetic energy of the entire transfer from the inner solar system out to Jupiter's distance. Jupiter's gravity helps pull you in, but that also makes you faster at closest approach, which means you typically have to remove a large amount of energy at just the right time. Doing that with propulsion requires substantial propellant, and carrying that propellant means either a larger launch vehicle or a smaller science payload. Missions that aim to Jupiter orbit often accept longer travel times, use gravity assists, or use clever multi-step approaches specifically so that the eventual capture is feasible within mass limits. Once you're in orbit, the payoff is massive. Instead of hours of close observation, you can conduct science for months or years, adjust your path, and repeatedly target regions of interest. But you pay for that privilege in energy, complexity, and often in calendar time. And then there's the third meaning, landing on a moon like Europa, which sounds like a small add-on. Jupiter, Europa, close enough, but is actually a major escalation. Europa is not just near Jupiter, it's deep inside Jupiter's gravitational environment, moving fast in a tight orbit and surrounded by a radiation and navigation context that forces careful planning. To land, you need to do all the things required for Jupiter arrival, plus additional steps. You must shape your trajectory to encounter Europa at the right place and time, match velocity with the moon, which is moving at high speed itself, and then perform a controlled descent onto a surface with its own hazards and limited prior ground truth. In many architectures, you don't go directly from interplanetary cruise to Europa landing. You first achieve Jupiter orbit or some form of capture, and then gradually adjust your orbit through a sequence of moon flybys to reduce relative speeds and target the moon you want. Each of those steps can add months or years because you're negotiating with orbital mechanics rather than brute forcing the solution with fuel you cannot afford to carry. Even within Europa mission, the definition matters. A Europa flyby, like repeated close passes from a Jupiter orbiter, can deliver high-value science without the full landing burden. A Europa orbiter must solve an additional capture problem, this time into orbit around Europa, while dealing with radiation exposure and frequent eclipses that complicate power and thermal control. A lander then must survive entry-like conditions, even without a thick atmosphere, execute precision guidance, and withstand a harsh environment on the surface. Each step up that ladder adds not only propulsion requirements, but also engineering mass, landing legs, descent engines, hazard avoidance sensors, more autonomy, and more redundancy. More mass pushes you towards slower, more efficient cruise profiles, or larger rockets, and those choices push the timeline again. So when someone asks how long would it take to go to Jupiter, a mission planner immediately answers with another question, silently in their head. Do you mean pass by, stay, or touch down? A flyby can be designed to emphasize transit speed because it doesn't need to pay the full braking bill. Orbit insertion forces you to care about arrival velocity and capture strategy, which often rewards longer, more efficient trajectories. Landing on a moon like Europa is a campaign objective, not a single sprint, and it typically demands staged operations inside the Jovian system to manage speed, targeting, and environmental constraints. And once you see that, the next concept becomes unavoidable. The reason these definitions matter so much is because space travel is not point and shoot. It's governed by the geometry and energy of orbits, and those orbits shape both the path you take and the time it takes to follow it. If go to Jupiter can mean anything from a drive-by to a full stop to a moon landing, the reason those options diverge so dramatically comes down to a simple but counterintuitive truth. Spacecraft almost never point at a planet and fly straight toward it like a bullet. In the solar system, motion is already happening at enormous speed. Earth is orbiting the sun at roughly 30 kilometers per second, and anything you launch from Earth inherits most of that motion. So the spacecraft doesn't start from rest, and it doesn't travel through a still environment. It starts on a moving platform inside a gravitational field, and every maneuver is really a negotiation with the orbit it already has. A good plain language way to think about it is that interplanetary travel is less like driving across a continent and more like changing lanes on a giant circular racetrack. Earth is in the 1AU lane, Jupiter is in a much wider lane, and your spacecraft begins in Earth's lane because it shares Earth's solar orbit. To reach Jupiter, you don't aim at Jupiter's current position. You change your orbit around the sun so that your new path stretches outward until it intercepts Jupiter's path at the same time Jupiter arrives there. That is why mission designers talk about trajectories as orbits and transfers, not straight lines. The spacecraft is essentially placed onto an elongated solar orbit, whose far ends reaches Jupiter's neighborhood, and then it coasts along that curve under the sun's gravity. Gravity is not just an obstacle here, it's the track. The sun's gravity shapes the arc you follow, and the planet's gravity tugs and bends your path locally as you pass through their neighborhoods. If you tried to go straight, you would have to continuously fight that gravity, spending fuel the entire time to maintain a line that nature doesn't want you to travel. That's not how we fly most missions, because fuel is mass is launch cost, and launch cost is mission feasibility. Instead, we do what nature allows. We give the spacecraft a carefully chosen change in velocity at departure, often a relatively short burn compared to the multi-year cruise, and then we let gravity do the long-haul steering for free. This is where the climbing a hill gradually instead of sprinting analogy fits. Think of Earth's orbit like a valley, and Jupiter's orbit like a higher ridge. To get from one to the other, you can't usually just sprint straight up the cliff face. That would require a huge burst of energy all at once, and you'd pay for it in rocket size and payload loss. The more efficient method is to take a path that gradually gains altitude, an energy-efficient climb that takes longer but costs much less effort. In orbital mechanics, altitude maps to orbital energy. Raising your solar orbit out to Jupiter's distance is like gaining altitude on that climb, and the most efficient routes are the ones that trade time for reduced fuel demands. This is also why distance is a misleading metric by itself. Two trajectories can cover roughly similar endpoint separations, yet one takes longer because it's a gentle, fuel-thrifty climb, and the other is shorter because it's a more aggressive push that demands far more energy. And it's why arrival speed becomes such a big deal. If you take the steep sprint, you tend to arrive with a lot of extra velocity you must deal with. If you take the gentler climb, you often arrive in a way that makes the next step, like orbit insertion, less punishing. Another plain language way to say it is space is not empty in the sense that you can ignore forces. It's a place where gravity is always acting, and the cheapest way to move is to cooperate with it. Most of the trip to Jupiter, the spacecraft is essentially falling around the sun on a new path that was selected at launch. The art is choosing that path so it intercepts Jupiter at the right place and time, with an arrival speed and geometry compatible with the mission goal, flyby, orbit, or moon operations. And that leads naturally into a practical constraint people rarely think about until they see real mission planning. If your path has to intercept Jupiter at a specific future point, you can't leave whenever you want. There are windows when the geometry makes that energy-efficient climb possible, and there are times when the alignment makes it unnecessarily expensive or slow. In other words, orbital mechanics doesn't just shape the route, it dictates the calendar. And that's why the next piece of the puzzle is launch windows and timing. Once you understand that a Jupiter-bound spacecraft is really being placed onto a carefully shaped solar orbit, the idea of a launch window stops sounding like a scheduling preference and starts looking like a hard physical constraint. You are not simply choosing a departure date, you are choosing the one moment when Earth is in the right place, moving in the right direction, so that a feasible transfer orbit will intersect Jupiter's path at the same time Jupiter gets there. If you launch too early or too late, the geometry changes and the trajectory you would need becomes more energetically expensive, longer, or sometimes impractical for the rocket and spacecraft you have. A good opportunity happens when Earth and Jupiter are aligned in a way that allows an efficient transfer, meaning the spacecraft can depart with a reasonable amount of energy and arrive after a predictable cruise time without requiring an oversized launch vehicle. Because Earth laps the Sun faster than Jupiter, the alignment between the two repeats on a cycle called the synodic period, which for Earth and Jupiter is a little over a year. That doesn't mean there is one perfect day each year, but it does mean there are recurring seasons when the geometry is broadly favorable and seasons when it is not. In favorable seasons, you can get a trajectory that is both energy efficient and operationally reasonable. Outside those seasons, you can still potentially go, but you pay. Higher departure energy, heavier rockets, reduced payload, or a longer travel time that increases cost and risk. This is why missing the window is not just inconvenient, it can be mission defining. If your spacecraft and rocket were designed around a certain energy budget, how much speed change you can afford at departure, then slipping the launch date by weeks can force a redesign of the trajectory, and slipping by months can push you into a fundamentally different set of options. Sometimes the new trajectory still works but adds months or years of cruise because you're forced into a less direct orbital arc that arrives later or requires extra intermediate maneuvers. Sometimes the new trajectory demands more energy than your launch vehicle can provide with the spacecraft mass you planned, which means you either remove payload, remove shielding, remove instruments, or accept a different propulsion stage. And sometimes, especially when gravity assists are part of the plan, missing the departure window breaks the entire sequence because the assist planet won't be in the right place at the right time anymore. So you aren't just waiting for Earth and Jupiter to realign, you are waiting for a multi-planet choreography to become possible again. Launch windows also exist in layers. There's the big picture window, weeks to months, when an Earth to Jupiter transfer is broadly efficient, but there are also narrow operational windows driven by real-world constraints, range safety, lighting conditions for tracking, power and thermal constraints, and the geometry needed for early communications. For certain mission designs, you might need the spacecraft to pass through specific regions of space at specific times, or avoid certain solar angles that would overheat hardware or starve solar panels. That can compress a season into a tighter set of dates that are truly usable. So when you hear that a mission launched in a window, it often means thousands of details converged: celestial mechanics, rocket performance, spacecraft readiness, and ground system availability. Timing matters at arrival too, not just departure. Jupiter's moons are moving quickly, and if your mission goal involves close passes of Europa, Ganymede, or Io, you may want to arrive when the moon geometry is favorable for the sequence of encounters you need. Arrive at the wrong time, and you may spend extra months reshaping your orbit to get the right moon flybys, or you may need additional fuel you didn't budget. In a flyby mission, arrival timing can determine whether you pass through the most interesting regions of the magnetosphere or see the desired hemisphere of a moon in daylight. For an orbiter, the arrival date can affect how quickly you can transition from capture to science operations. In other words, the calendar is embedded into the physics from beginning to end. All of this explains a key reality behind any "how long to Jupiter" answer. The travel time is not only about engine performance, it's also about when you can leave efficiently. A mission that could take a shorter time on paper may not be available on the day you're ready to launch. Conversely, a mission may accept a longer cruise because the available window makes that plan robust and affordable. And once timing is on the table, the next question becomes irresistible. If you want to shorten the cruise, what does fast actually require in terms of departure energy, rocket capability, and trade-offs? That's where the fastest plausible trajectories come in, because speed is never free in orbital mechanics. It's always purchased with something else. Launch windows determine when you can leave efficiently, but once you are inside a workable window, the next lever people instinctively reach for is speed. Okay, but what's the fastest plausible way to get there? The answer is straightforward in principle and brutal in practice. You can shorten the trip by leaving Earth with much higher departure energy, meaning you inject the spacecraft onto a more aggressive solar trajectory that reaches Jupiter's distance sooner. In mission design language, you are paying for a higher hyperbolic excess at Earth and typically arriving with a higher relative velocity at Jupiter. In plain terms, you are throwing the spacecraft harder so it gets there faster, but the bill shows up everywhere else in the mission. The first trade-off is rocket capability. Higher departure energy means the rocket must deliver more speed to the spacecraft. Rockets do not scale gently with speed demands. Small increases in required performance can translate to large increases in launch mass, cost, and complexity, especially if you are already near the upper end of a rocket's capability. If you hold the rocket fixed, the usual way to buy more departure energy is to reduce payload mass. Fewer instruments, smaller antennas, less propellant for later maneuvers, less shielding, less redundancy. That can be acceptable for a small probe whose goal is a quick flyby with minimal hardware. It is much less acceptable for a flagship science mission, and it becomes deeply problematic for human missions where mass is dominated by life support, habitat volume, radiation protection, and safety systems. The second trade-off is propellant and staging. If the launch vehicle alone cannot provide the energy you want, you can add an upper stage or a dedicated departure stage that performs an additional burn after reaching parking orbit. This can push the spacecraft onto a higher energy escape trajectory, but it adds mass and complexity, and it forces hard choices about what rides along. Extra stages also raise integration risk, increase the number of critical events, and can constrain launch operations. The fast plan may look clean on a whiteboard, but in practice, it often becomes a chain of tight margins. More performance required at launch, more sensitivity to small errors, and less flexibility if something goes slightly off normal. The third trade-off is the one that surprises non-specialists. A faster trip usually means a harsher arrival. If you sprint to Jupiter, you tend to arrive with greater speed relative to the Jovian system, which can be fine, essentially ideal, if the mission is a flyby because you do not need to stop. You can accept a high-speed encounter and focus on collecting data in a short window. But if your mission definition requires entering Jupiter orbit or performing controlled operations around the moons, arriving fast is a problem you must later solve with braking. And braking is expensive. The faster you arrive, the more energy you must shed to be captured. And that typically means more propellant, a more complex sequence of gravity assists, or clever but risky approaches like deep atmospheric passes, which bring their own hazards. In other words, a fast cruise can be paid for twice, once when you depart Earth and again when you try to slow down at Jupiter. Fast trajectories also impose operational and engineering stress. High-energy launches can increase vibration and thermal environments, which affects spacecraft design. Aggressive timelines compress commissioning and checkout phases, leaving less margin to diagnose and recover from early anomalies. A spacecraft on a high-energy path may have fewer mid-course correction opportunities and narrower arrival corridors because higher speeds reduce the time available to correct trajectory errors. This is especially significant for missions that require precision targeting, like threading the needle between Jupiter's radiation belts or arriving at a specific geometry for a moon encounter. The faster you go, the more unforgiving the geometry becomes. Then there is the payload triangle that shows up immediately. For a given rocket and mission concept, you are trading among time, mass, and capability. Want to arrive sooner? You either need a stronger rocket, a lighter spacecraft, or more staging or propellant devoted to departure. But a lighter spacecraft often means fewer instruments, less power generation, smaller communication systems, or reduced shielding, each of which can undermine the very reason you went to Jupiter. And if you add propellant to go faster, you are increasing mass, which may force you to remove payload anyway to stay within launch constraints. Fast is therefore rarely the default choice for robotic science missions, unless the mission objective explicitly demands it, because scientific return usually benefits more from carrying robust instruments and operating for longer at Jupiter than shaving months off cruise time. For humans, the trade-offs tighten further. A high-energy, short-duration sprint sounds attractive because it reduces exposure to microgravity and deep space radiation during transit. But achieving that sprint with a human-rated mass is extraordinarily demanding. If you try to buy speed by cutting mass, you are cutting into life support margins, shielding, redundancy, or habitability, areas where you cannot safely compromise. If you try to buy speed with more propellant, your vehicle grows heavier, which makes it harder to accelerate, which pushes you into huge launch stacks or in-space assembly and refueling. In practice, fast for humans is not merely a trajectory choice, it is an architecture choice that ripples through launch strategy, propulsion technology, and risk posture. So the fastest plausible style of trajectory is best understood as a premium option. It can shorten the cruise, especially for smaller robotic payloads or flyby style missions, but it demands high departure energy that must be purchased with bigger rockets, additional stages, reduced payload, tighter margins, and often a more punishing arrival that complicates anything beyond a brief encounter. And that naturally raises the next question. If fast is expensive and unforgiving, why do so many missions deliberately choose to be slower? The answer is that there is a well-behaved, energy-efficient family of paths that mission planners trust because it saves propellant, increases payload, and improves robustness, even if it makes you wait longer to reach Jupiter. If the fastest plausible approach is essentially paying a premium to throw the spacecraft harder and accept the consequences, the more common philosophy in deep space mission design is the opposite. Spend less propellant, keep more payload, and buy reliability with a gentler trajectory, even if it means a longer cruise. This is where the idea of a Holman-like transfer comes in, not as a rigid template that every mission follows, but as a conceptual backbone for why slow is often the rational choice. A classic Holman transfer is the most fuel-efficient two-impulse route between two circular orbits. You perform one burn to place yourself on elliptical orbit that reaches the target's distance, and another burn at arrival to match the target's orbit. For Earth to Jupiter, the pure textbook version is complicated by real-world factors, planetary inclinations, launch site constraints, non-circular orbits, and mission-specific arrival goals. But the core intuition remains. The cheapest way to climb from Earth's solar orbit to Jupiter's is to take a long, smooth arc that naturally reaches out to Jupiter's orbital neighborhood. Why does that save propellant? Because in orbital mechanics, changing your orbit is fundamentally about changing your energy relative to the body you orbit, in this case, the Sun. The more abruptly you try to raise your orbit, the more speed change you need, and speed change is what propellant buys you. A Holman-like approach asks for a departure that is energetic enough to lift your solar apophysis outward to Jupiter's distance, but not so energetic that you arrive with an extreme relative velocity. You are climbing the hill at the pace that minimizes fuel expenditure. The resulting cruise time is longer, often measured in years for Jupiter missions, but it's long in a controlled, predictable way, and that predictability is a form of reliability. Mission planners accept these longer cruise times for three practical reasons that matter as much as the physics. First, mass efficiency translates directly into science. If you can achieve your trajectory with less propellant or lower departure energy requirements, you can allocate mass to instruments, power systems, radiation shielding, communication hardware, and redundancy. For a Jupiter mission, those are not luxuries, they are mission enablers. A larger antenna can return more data from farther away. More power margin can support higher duty cycle instruments and heaters in deep space. More shielding can keep electronics alive in Jupiter's radiation environment. In many cases, the science return from a more capable payload dwarfs the value of arriving a few months earlier. Second, slower, efficient trajectories often provide larger operational margins. High-energy, fast transfers can be sensitive to small navigational errors because a spacecraft is covering more distance per unit time and has less time to correct course before critical events. A longer cruise typically provides more opportunities for mid-course correction and trajectory refinement, and it spreads risk across time rather than stacking it into a narrow arrival corridor. This matters because interplanetary navigation is not a one-and-done calculation. It is a process of iterative refinement using tracking data, small correction burns, and continuous estimation of spacecraft state. Missions that are not living on the edge of performance can afford conservative correction budgets and maintain healthy propellant reserves for later phases, especially important if the mission goal is orbit insertion or complex moon tours. Third, and often overlooked, slower trajectories can reduce the severity of the arrival problem. Even if you don't do a perfect home and capture, arriving with a lower relative velocity can simplify the energy you must remove to enter orbit around Jupiter or to set up subsequent moon encounters. For orbiters, that can translate into a feasible capture burn size and a manageable propellant budget. For missions that plan to use Jupiter's moons to reshape their orbits, a less aggressive arrival can make those sequences easier to design and less punishing on the spacecraft. In essence, a longer, more efficient cruise can be part of paying down risk and complexity later, when the environment becomes harsher and the mission is less tolerant of mistakes. This is why many typical Jupiter missions are not designed around the shortest travel time, but around the best overall mission value. Maximize payload capability, minimize required launch performance, preserve propellant for operations, and keep the trajectory robust to real-world uncertainties. In programmatic terms, it's also a budgeting and schedule reality. Launch vehicles, spacecraft mass, and propulsion stages are expensive and hard to change late in development. A Hohmann-like energy-efficient trajectory often fits within a broader set of constraints that are stable and fundable, whereas a fast trajectory can force upgrades. Bigger rockets, more staging, more mass shaving that cascade into cost growth and risk. There is, however, one major reason why the efficient but slower approach does not always mean a single smooth arc from Earth to Jupiter. Mission designers have a way to keep propellant demands low while still achieving the required energy changes by borrowing energy from other planets. That trick can make the route longer in distance and time, but it can make the mission possible when a direct, efficient transfer is still too demanding. And that brings us to the most famous piece of interplanetary strategy: gravity assists, the cheat code that lets you trade time and geometry for speed without carrying extra propellant. That efficiency-first mindset is exactly where gravity assists enter the story, because they let mission designers pull off something that feels like a loophole: change a spacecraft's speed and direction significantly without carrying extra propellant for the full change. A gravity assist is not a free energy in the magical sense, but it is a very real way to rebalance energy inside the solar system by borrowing a tiny amount from a planet's orbital motion. When you hear people call it a cheat code, what they mean is that it can turn an otherwise impossible mission, too heavy, too underpowered, too propellant limited, into a feasible one by letting gravity do part of the acceleration job. Here's the plain language version. Planets are moving around the sun at tremendous speeds, and they carry a huge reservoir of momentum. During a close flyby, a spacecraft falls into a planet's gravitational well and then climbs back out. In the planet's own frame, the spacecraft leaves with roughly the same speed it arrived with. Gravity is conservative that way. But in the sun's frame, the spacecraft can leave with a different speed and direction because the planet itself is moving. If you pass behind the planet relative to its direction of travel, you can effectively steal a little of its orbital energy, leaving the flyby with a higher heliocentric speed. If you pass in front, you can give some energy back, slowing down in the sun's frame. The planet's orbit changes too, but by such an absurdly tiny amount that it's practically undetectable, while the spacecraft feels the difference dramatically because it's so small by comparison. This matters for Jupiter missions because the fundamental challenge is energy. Raising a spacecraft from Earth's solar orbit out to Jupiter's distance demands a big change in orbital energy, and doing all of that with fuel you carry is expensive in mass. Gravity assists let you stack smaller, cleverly timed boosts. A common pattern is to use Venus and/or Earth flybys to increase heliocentric energy step by step, or to reshape the trajectory so that the eventual Jupiter transfer requires less launch energy than a direct departure would. The spacecraft might launch into an initial orbit that is achievable with the available rocket, then use a series of planetary encounters to ratchet its solar orbit outward until Jupiter becomes reachable with the desired arrival geometry. In that sense, gravity assists are like getting several pushes on a swing at exactly the right moments, rather than trying to jump to the maximum height in one exhausting leap. Gravity assists can also be used not just to speed up, but to aim. Changing direction is expensive if you do it with engines, because a large plane change or bend in trajectory requires significant delta V. A close planetary flyby can swing your path like a slingshot, delivering a big change in heading without spending propellant. For missions that need specific approach angles, say to thread between radiation hazards, to target a particular moon's orbital plane, or to set up a complex tour through the Jovian system, this directional control can be just as valuable as the speed change. But the cheat code has a very real price, and it shows up on the calendar. Gravity assists are only available when the planets are in the right places at the right times, and the route is rarely a straight shot outward. A spacecraft might dive inward towards the Sun to reach Venus for an assist, then swing back out past Earth for another, then finally head toward Jupiter. That can mean a path that is longer in distance and often longer in time, even if it is dramatically cheaper in propellant. In other words, gravity assists frequently trade time and geometric complexity for mass efficiency and feasibility. If a direct trajectory is the express train, expensive ticket, fewer stops, gravity assists are the multi-transfer route. More connections, more waiting for the right departures, but far less expensive overall. They also increase mission complexity in ways that matter to reliability. Each flyby is a high-stakes navigation event with tight timing and tight geometry. You must arrive at a precise point in space at a precise time because being off by a small amount can cascade into a large miss later. And because the assists are chained, an early navigational error can propagate forward, shrinking your margins at later flybys. Mission teams mitigate this with careful tracking and mid-course corrections, but it is still a complexity cost. More critical events, more operational planning, more opportunities for something to go wrong. That said, gravity assists are used so often precisely because they are a proven, mature technique. Complex, yes, but routinely managed. There is also a subtle reality about faster that gravity assists complicate. A gravity assist can absolutely increase your heliocentric speed, but the overall travel time can still be longer if the assist sequence forces you to wait for planetary alignments or follow an indirect route. This is why you sometimes see mission timelines that sound counterintuitive. We're going to Jupiter, but first we're heading towards Venus, or we'll pass Earth again after launch. That is not wandering, that is strategic energy management. The spacecraft is using the inner planets like stepping stones to build the exact orbit it needs at a mass and cost that fits within the launch vehicle and the mission budget. So gravity assists earn their reputation. They let spacecraft add or subtract speed and bend trajectories without hauling the equivalent fuel, and they can enable missions that would otherwise require unreasonably large rockets or unacceptable payload cuts. But the route is often longer, the timing is more constrained, and the operations are more intricate. And that naturally sets up the next question. If gravity assists and efficient transfers often stretch the trip into years, what does history suggest is normal for real Jupiter missions when you balance costs, capability, and risk? Gravity assists and efficient transfers can make the route feel like a detour, but they also reveal what normal looks like when you're designing a mission that has to close financially, technically, and operationally. In practice, the most cost-effective robotic missions to Jupiter tend to accept multi-year cruise phases, not because engineers enjoy waiting, but because the mass and energy savings buy you the things that actually make the mission succeed: power margin, radiation protection, a stronger telecom link, robust propulsion reserves for corrections and science operations, and instruments that don't have to be shaven down to meet an aggressive departure energy target. You can see the spread clearly if you separate flybys from orbiters. The early reconnaissance-style flybys could be comparatively quick, on the order of about 1.5 to 2 years, because they were optimized to arrive fast and not stop. For example, Voyager 1 launched on September 5, 1977, and reached Jupiter for its closest approach on March 5, 1979, roughly a year and a half later. Voyager 2 launched August 20th, 1977, and reached Jupiter on July 9th, 1979, just under 2 years. Pioneer 10 launched in early March 1972 and made its closest Jupiter approach in early December 1973, again, roughly a 21-month class trip. Those faster timelines are real, but they're also tied to flyby objectives, high departure energy, and mission eras where the arrive fast and keep going model fit the goals. When you shift to what most people picture as a full Jupiter mission, meaning you intend to operate for a long time in the Jovian system, the typical travel time often lands in the 5 to 6 year range, sometimes longer, because you're designing for arrival conditions you can live with, not just arrival speed. Juno is a clean modern example. It launched on August 5, 2011, and arrived to enter Jupiter orbit on July 4, 2016, a 5-year cruise that balanced launch capability, spacecraft mass, and an orbit insertion plan that could be executed reliably. That time frame is a sweet spot for many robotic orbiters, long enough to allow energy-efficient routing and manageable arrival speeds, but not so long that operations and component aging dominate the risk picture. Some missions stretch beyond that, and that's not a failure. It's a deliberate cost and feasibility choice, driven by launch energy limits and complex science goals. Galileo, for instance, launched October 18, 1989, and didn't begin orbiting Jupiter until December 1995, a cruise of about 6 years that relied on a gravity assist strategy rather than an ultra-high energy direct injection. On the current horizon, the pattern continues. Europa Clipper is planned as a long-haul gravity assist journey. NASA describes it as traveling about 1.8 billion miles to reach Jupiter in April 2030, which corresponds to roughly 5.5 years from its 2024 launch. ESA's JUICE mission goes even further into the efficient but longer category, with a multi-flyby route toward a July 2031 Jovian arrival, an extended cruise that reflects both the mission's heavy science payload and the realities of energy-efficient delivery to Jupiter's system. So, if you're looking for an honest, typical range that reflects how mission planners usually balance budget, risk, and capability, it's this. Flyby-style missions can be around 2 years, but the common, cost-effective robotic approach, especially for orbiter and long campaigns, clusters around 5 to 8 years, depending on launch energy, gravity assist opportunities, and what the spacecraft must still accomplish after it arrives. The headline lesson is that several years isn't a sign of sluggish engineering. It's often the most rational way to maximize payload and reliability while keeping the propulsion problem solvable with real rockets and real mass constraints. And that sets up the next step in the story, because the moment you replace robotic probe with crew, the same trait space doesn't just shift, it tightens dramatically as human life support, shielding, redundancy, and abort capability turn typical Jupiter timelines into a fundamentally different equation. That several years is normal framing works cleanly for robots because robots are, by design, tolerant of being treated like cargo. They can hibernate, sip power, accept single-string subsystems in places, and take calculated risks because the mission's success criteria is scientific return, not guaranteed survival. The moment you put people on board, how long to Jupiter stops being primarily a trajectory question and becomes a systems engineering and risk management question, because humans turn the spacecraft from a lightweight instrument platform into a self-contained, fault-tolerant habitat that has to keep functioning every minute of the journey. Start with the obvious. Life support is not a single box you bolt on. It is air revitalization, CO2 removal, oxygen generation or storage, humidity control, temperature management, water recovery and storage, waste handling, food storage and preparation, medical capability, and the power, spares, and maintenance access to keep all of that running continuously. Then add volume and habitability, because a crew cannot be packed into the tight, minimal structure that's acceptable for a probe. You need space to sleep, work, exercise, and isolate in emergencies. You need radiation-safe areas. You need acoustic and thermal comfort. You need equipment arranged for maintenance, not just launch packaging. Every cubic meter costs mass, structure, and shielding, which costs propulsion performance. Now add the part that bites hardest: shielding and redundancy. A robotic spacecraft can sometimes accept radiation-hardened electronics, clever fault protection, and limited shielding, because if a subsystem degrades, you might limp through and still do meaningful science. A crewed vehicle cannot take that posture. People need shielding against chronic exposure, galactic cosmic rays, and episodic events, solar particle events, and shielding is fundamentally mass. You can be clever, use water and supplies as storm shelter mass, shape the habitat, optimize materials, but at the end of the day, meaningful radiation protection is heavy. Meanwhile, redundancy is not optional. You don't just duplicate one computer, you duplicate critical life support chains, power conditioning, thermal loops, communications, guidance, and often propulsion fault tolerance. And redundancy is not only extra hardware, it's extra spares, extra tools, extra diagnostics, and extra training time and procedures to keep the system maintainable over years. This is exactly why going fast becomes harder with humans, even though faster is desirable. Rocket physics is unforgiving. To shorten the trip, you generally need more departure energy, which means more propellant and/or more powerful stages. But the crewed vehicle is already heavy because it's carrying the things that keep humans alive and safe. If you try to add the propellant needed for a truly fast transit, mass balloons. If mass balloons, the rocket and stages must grow. If the rocket grows, the mission architecture shifts toward multiple launches, on-orbit assembly, and higher operational complexity. In other words, the crew pushes you toward a large vehicle, and fast pushes you toward even more propulsion mass, and those two demands reinforce each other in the worst possible way. Robots can accept the fast but light bargain. Humans typically cannot, because light often means cutting precisely the margins that keep a crew alive. Then there's the question of abort options, which quietly rewrites the entire timeline logic. Most robotic missions are commit and continue. If something fails after departure, you do contingency operations and hope to salvage partial success. Human missions generally need credible abort modes, ways to preserve life when something goes wrong. For nearby destinations, abort can mean turn around or come home quickly. For Jupiter distances, abort is not a simple mid-course U-turn. It's a long-duration survival problem. If you plan a slow, multi-year cruise, your abort case is essentially keep the crew alive for years while limping home, which demands even more consumables, spare parts, and robust systems, adding more mass. If you plan a faster transit, you reduce exposure time, but you may also reduce flexibility because high-energy trajectories can be less forgiving and can complicate return opportunities. Either way, abort isn't a footnote, it's a first-class design driver that adds mass, complexity, and constraints, all of which feed back into how fast you can plausibly go. Human factors also change what time even means operationally. A probe can coast in a stable thermal attitude with minimal interventions for months. A crewed mission requires constant monitoring, maintenance, exercise, psychological support. That increases operational workload, increases the probability of wear-out failures simply because more systems are running continuously, and increases the consequences of small problems. A robotic spacecraft can accept single-point failures in certain subsystems. A crewed vehicle tries to eliminate them, and eliminating them is expensive in mass. So while a robotic mission can choose a trajectory mainly for propellant efficiency and payload delivery, a crewed mission must treat the trajectory as one lever among many in a broader system of systems optimization: transit duration versus radiation exposure, vehicle mass versus propulsion capability, redundancy versus launch feasibility, and mission flexibility versus high energy commitment. The result is a hard, practical tension. Humans create strong reasons to want shorter transit times, less microgravity exposure, less cumulative radiation, less psychological strain, but the very measures required to keep humans safe make the spacecraft heavier, and that makes shorter transit times harder to purchase with chemical propulsion and conventional architectures. That is why discussions of humans to Jupiter so quickly pivot from how long to what propulsion, what shielding strategy, what in-space assembly, what power source, what abort posture. Because without those answers, a single travel time number is mostly fantasy. And if that sounds like the schedule is being squeezed from both ends, it's because it is. You're trying to go faster to protect the crew, but the protective measures make you heavier and slow you down unless you change the propulsion or mission architecture. Which leads directly to the next constraint that is uniquely punishing around Jupiter, not just the radiation accumulated during the cruise, but the intense radiation environment waiting at arrival, where the design has to control not only how you travel, but how you approach, where you linger, and how long you can safely operate. That tension between go faster to protect the crew and go heavier to keep the crew safe gets even sharper at Jupiter because the planet is wrapped in a hazard that doesn't look like a hazard until it starts breaking hardware and raising dose: radiation. Jupiter's magnetic field is enormous, and it traps charged particles into intense radiation belts that are in practical mission terms closer to a high-energy particle accelerator than to the relatively mild space environment many spacecraft experience closer to Earth. This is why radiation becomes an invisible schedule killer, because it doesn't just threaten the mission in the abstract, it forces very specific choices about where you can fly, how long you can linger, and what kind of orbit is even survivable. The key idea is that arriving at Jupiter is not like arriving at Mars, where the environment is harsh but comparatively steady and navigable. At Jupiter, the danger is highly structured in space. Some regions are dramatically worse than others, and the difference can be mission-defining. Close to the planet, especially in certain orbital zones, radiation levels rise sharply. Meanwhile, Jupiter's inner moons sit in different parts of that environment. Io's neighborhood is notoriously hostile, Europa's region is still severe, Ganymede and Callisto are generally more forgiving by comparison. That geography means you cannot plan trajectories purely for convenience. You plan them to control dose accumulation over time for both electronics and, in the human case, bodies. Time becomes a consumable. Every hour spent in the wrong region is not just time passing, it is measurable damage and risk accumulating. For robotic missions, this reality shows up first in spacecraft design, then in trajectory design. You harden components, add shielding where it matters, and build fault protection that can reset systems when radiation flips bits in memory or triggers spurious signals. But shielding is mass, and mass competes with propellant and payload. So after a point, the most powerful mitigation is simply not being there, not dwelling in the harshest zones any longer than necessary. That drives orbit selection. Instead of parking a spacecraft in a tight, low-altitude orbit that repeatedly plunges through the worst of the belts, mission designers often choose elongated orbits that spend most of their time far from Jupiter and then dive in briefly to collect close-in data before retreating back out. You end up with science plans built around short peri-Jove passes and longer safe distance arcs because that orbit geometry is a radiation strategy as much as it is a navigation strategy. Radiation also changes the meaning of approach. In a purely geometric sense, you might imagine approaching Jupiter on the most direct line for a quick arrival. In reality, you may deliberately choose an approach corridor that reduces time in hazardous regions, even if it slightly increases complexity. The spacecraft's arrival geometry, its direction, its inclination relative to Jupiter's equator, and how close it comes on the first pass can influence how deeply it penetrates into the most intense belt. You'll see mission designs that look counterintuitive until you remember the invisible constraint. The objective is not merely to arrive, but to arrive in a way that preserves the spacecraft's ability to function long enough to do the mission. When the goal includes Europa, radiation becomes even schedule sensitive. Europa is one of the most scientifically compelling targets in the solar system, but it lives in a region that is punishing for electronics, and by extension, punishing for mission timelines. A Europa-focused mission often avoids a hangout near Europa continuously posture because continuous proximity can be too costly in dose. Instead, the strategy tends to emphasize repeated fast flybys. You dip in, collect data, and leave, stacking science over many brief encounters while keeping cumulative exposure within a survivable envelope. That architecture has a direct timeline implication. You may need many orbits and many passes to build up the data set you want, because a spacecraft cannot afford to loiter in the environment that would make data collection easier. So radiation doesn't just threaten survival, it shapes the cadence of the entire mission. For humans, the implications are even more restrictive because Jupiter's radiation belts are not merely an electronics concern. They become a crew safety constraint that can dominate operational planning. A crewed vehicle would require much more substantial shielding, and likely strict operational rules about where the crew can be during certain phases. For example, being in a heavily shielded storm shelter volume when passing through higher radiation regions. But even with shielding, the basic logic remains: minimize time in the harshest regions. That pushes crewed mission concepts away from Jupiter orbit operations in the inner system and toward architectures that either remain farther out in safer orbital zones or focus on destinations like the outer moons where the environment is less extreme. In other words, radiation doesn't just affect how long it takes to reach Jupiter, it can affect what a plausible human mission to Jupiter is allowed to be at all. This is why radiation acts like a schedule killer rather than a simple design parameter. If you need to reduce exposure, you may choose trajectories that avoid repeated deep belt crossings. If you need to reduce exposure during science operations, you may change orbit shapes, shorten close approaches, increase the number of orbits, or alter the sequence of moon encounters, all of which can change mission duration and timeline structure. And because radiation risk increases with time spent in the wrong place, how long becomes entangled with how often and how deep. How often you dip into the belts, how deep you go, and how long you stay each time. And once radiation is dictating your approach corridors, orbit shapes, and operational cadence, there's another invisible timing constraint that starts to matter more and more as you get farther from Earth: the simple fact that commands and data don't travel instantly. The growing communication delay changes how you operate spacecraft in complex, hazardous environments, pushing more autonomy on board and shaping the rhythm of mission decisions, which is why the next piece of the Jupiter timeline puzzle is communications lag and control. Radiation forces you to choreograph where you fly and how long you linger. But even when you've picked the safest possible path, Jupiter adds another constraint that quietly reshapes the entire mission rhythm. You can't drive it in real time from Earth. By the time a command reaches the spacecraft and a confirmation returns, the moment you are responding to is already long gone. At Jupiter distances, the one-way speed of light delay is typically tens of minutes, commonly quoted at roughly about 33 minutes at closer alignments and about 54 minutes when farther. That means a round-trip ask and answer loop is often well over an hour, and that single fact changes how you plan operations, how you design software, and, indirectly, how long missions take to execute their objectives. The most important operational consequence is simple: operators can't joystick Jupiter. If a spacecraft is approaching a moon flyby, skimming through a radiation hotspot, or executing a critical burn, ground control cannot wait to see a problem and then react in the moment. Any real-time intervention would arrive too late. Instead, the spacecraft must be able to detect conditions, make decisions, and protect itself autonomously. That autonomy can be as basic as fault detection and safing, resetting computers, switching to backups, repointing to protect sensitive instruments, or as sophisticated as onboard navigation, hazard assessment, and timing adjustments around pre-planned events. Either way, autonomy is not optional at Jupiter. It's a prerequisite for safe and effective operations. Autonomy, however, is not free capability. It increases mission complexity in ways that feed back into timelines. More autonomy means more software, more testing, more simulation, and more operational rehearsal before launch. It means you invest significant effort in defining decision authority, what the spacecraft is allowed to do on its own, what it must never do without ground approval, and how it behaves when sensors disagree or data is ambiguous. That work is time-consuming because the stakes are high. An overly timid autonomy system may save too often and interrupt science, while an overly aggressive one may make a wrong call at the worst time. For Jupiter missions, where radiation can induce spurious signals and temporary upsets, getting that balance right is particularly delicate. The light time delay also changes the cadence of routine mission operations. Near Earth, a team can iterate quickly. Command, observe telemetry, adjust, repeat. At Jupiter, every iteration is slow. If you send a complex command sequence and discover a parameter was slightly wrong, you don't correct it in minutes, you correct it after the delay, then wait again to verify. So teams tend to rely on longer command loads, batches of pre-planned instructions, and on carefully scripted timelines that the spacecraft can execute with minimal intervention. That style improves safety, but it also means that operations become less flexible and more procedural. And procedural operations, by their nature, can lengthen how long it takes to complete a campaign of observations, because you spend more time planning and validating each sequence to avoid needing multiple slow back-and-forth cycles. Communications limitations compound the issue. At Jupiter's distance, signals are weak and data rates are often constrained by power, antenna size, and the capabilities of Earth's ground network. With limited bandwidth, you can't always downlink everything you'd like immediately. Missions often store data on board, prioritize what to send first, and schedule downlinks around Earth station availability and spacecraft pointing constraints. That becomes another subtle timeline driver. Even if the spacecraft collects data quickly during a fast flyby, it may take days or weeks to return the full dataset to Earth, and mission planning may wait for key subsets of that data before committing to the next sequence. The science timeline becomes gated not just by where the spacecraft goes, but by how quickly insight can be extracted and fed into future decisions. This is also why autonomy matters beyond safety. It matters for productivity. If the spacecraft can perform onboard event detection, for example, flagging unusual features, compressing data intelligently, or prioritizing certain observations, it can make better use of limited downlink and reduce dependence on slow, human-in-the-loop decisions. But building that capability adds development and validation burden, which is one reason ambitious outer planet missions can take so long to mature. You're not only engineering a spacecraft to survive, you're engineering an operations model that works when human reflexes are effectively an hour behind. The net effect is that light time delay doesn't usually add years to the cruise itself, but it raises the cost of mistakes and slows the pace of iterative decision-making, which can stretch operational timelines once you arrive, especially in complex campaigns involving repeated moon flybys, radiation avoidance tactics, and delicate orbit adjustments. And that feeds directly into the next reality that surprises most people. Even if you could communicate instantly, arriving isn't the finish line, because the hardest part of many Jupiter missions is not getting there. It's slowing down enough to do anything useful once you're in the system. All of the earlier pieces, moving target distances, efficient arcs, gravity assists, radiation avoidance corridors, and light time delay, lead to a reality that quietly dominates Jupiter mission design. Arrival is not done, because arriving means you show up moving extremely fast, and physics does not give you a free brake pedal. In everyday travel, getting there implies you can slow down at the destination with little consequence. In interplanetary flight, your spacecraft reaches Jupiter carrying the accumulated energy of a long fall through the sun's gravity well, plus whatever extra energy you injected at departure. By the time you reach Jupiter's neighborhood, you're not drifting gently into a parking spot. You're on a trajectory that is often screaming past the planet unless you actively remove a huge amount of energy at precisely the right time. This is the braking problem in its simplest form. To arrive and stay, you must reduce your speed relative to Jupiter enough that Jupiter can gravitationally capture you into orbit. If you don't slow down, Jupiter's gravity will still tug you, bend your path, and potentially slingshot you into a different solar orbit, but you will not be bound to the planet. A flyby mission can treat that as a feature, come in fast, collect data during closest approach, and continue onward. But the instant your goal becomes Jupiter Orbiter or Europa campaign, braking becomes one of the largest line items in the mission's energy budget. The reason this is so punishing is that slowing down requires delta V, and delta V is purchased with propellant or with some other mechanism that effectively removes energy. Carrying propellant all the way from Earth is expensive because every kilogram of propellant requires more propellant to push it, and the rocket equation compounds that penalty. So the more you plan to brake at Jupiter, the more mass you must allocate to fuel and engines, which either demands a larger launch vehicle or forces you to cut payload and shielding, often the very things you went to Jupiter to bring. This is why fast cruise can be a trap. If you sprint to Jupiter and arrive with even more velocity, you have made the braking problem worse, and you may end up spending more mass and complexity on capture than you saved in time. Because of that, many missions deliberately choose architectures that avoid paying the full braking bill in one go. One option is simply to choose a flyby, because it avoids the need to shed enormous energy at arrival. Flybys can still deliver extraordinary science, especially for reconnaissance and broad surveys, but they inherently limit your observation time near the system. Another option is to arrive on a trajectory that makes capture more manageable, accepting a longer cruise or a more complex route so that the arrival speed is lower and the required capture maneuver is smaller. This is one practical reason efficient but slower transfers are so common. They're not just about saving fuel on the way out, they're about arriving in a state you can actually work with. A third family of solutions is to use complex assist sequences inside the Jupiter system. Jupiter has large moons that function like miniature planets for navigation purposes, and repeated flybys of those moons can be used to reshape an orbiter's path without spending as much propellant as direct engine burns would require. In effect, you can use the moons to trade one kind of orbit for another over time, adjusting your energy and geometry step by step. The trade-off is again time and complexity. Moon tour trajectories can take months to years to evolve into the exact orbit you want, and they demand careful planning, high navigation precision, and robust autonomy because the system is dynamic and the environment is harsh. There are also more aggressive braking ideas that appear in studies and advanced concepts, such as using a planet's atmosphere to remove energy, aero capture, or aero braking. In principle, dipping into Jupiter's upper atmosphere could shed large amounts of speed without carrying the equivalent propellant. In practice, Jupiter's atmosphere introduces severe engineering risk, extreme heating, uncertain atmospheric density profiles at the relevant altitudes, tight corridor requirements, and a general lack of tolerance for error. For robotic probes, it can be a high-risk, high-reward approach. For crewed missions, it is typically considered even more daunting because the safety margins must be much larger and the consequences of a bad pass are unacceptable. So while atmospheric braking can look like an elegant workaround on paper, most real mission designs lean toward strategies that are more controllable, even if they take longer. This is why the phrase, "we're going to Jupiter," can conceal two fundamentally different mission profiles with radically different clocks. If go means a flyby, the mission can prioritize transit time and accept a high-speed arrival because it doesn't need to stop. If go means orbit, the trajectory is often selected to make capture feasible within mass limits, which tends to push designs toward longer cruises, gravity assists, or moon tour sequences that trade calendar time for propellant savings. And if go means Europa operations or landing, the braking challenge multiplies. You must not only manage Jupiter arrival, but also manage your relative velocity within the Jovian system to set up repeated moon encounters or to match speeds for orbiting and descending. In other words, the braking problem is the bridge between reaching Jupiter's neighborhood and doing anything meaningful once you're there, and it is one of the main reasons travel time answers swing so widely. And once you see braking as an energy and mass problem rather than a simple slow down when you arrive step, the next constraint snaps into focus. Every choice you make is a trade among fuel, time, and payload. You can carry more propellant to go faster or brake harder, but that steals mass from instruments and safety systems. You can take more time to reduce propellant needs, but that increases operational cost and exposure. And you can shrink payload to fit the rocket, but that can undercut mission goals, especially for human missions, where payload includes survival. The braking problem makes it clear that time to Jupiter is never just a distance question. It is an accounting problem, and the currency you keep spending is mass. That's where the fuel, time, payload triangle comes in, because nearly every trajectory decision ultimately collapses into the same three-way trade. If you want less time, you typically need more speed. More speed typically requires more propellant, or more energetic staging, and more propellant usually forces you to cut payload. You can bend the triangle at the edges with clever trajectory design, gravity assist, or advanced propulsion, but you can't repeal it. Something always gives. Start with the first edge. More speed usually means more propellant. To shorten the cruise, you need a higher energy departure that raises your solar orbit faster and often delivers a higher arrival velocity. That energy does not appear spontaneously. With conventional propulsion, it is purchased through propellant mass and engine performance. Even when the launch vehicle provides much of that energy, the same logic holds. The rocket must spend propellant to give the spacecraft a higher injection speed. If you demand a faster transfer while keeping everything else constant, you raise the performance requirement at launch, and performance requirements are paid in propellant, bigger stages, or both. Now the second edge. More propellant means less payload, because your launch capacity is finite. For a given rocket, total delivered mass to a Jupiter-bound trajectory is limited. If you allocate more of that mass to fuel and propulsion hardware, you must take it away from something else: scientific instruments, communication systems, radiation shielding, structural margin, redundancy, thermal control hardware, or onboard power generation. The trade is especially sharp because propellant tends to crowd out everything else. You don't just add fuel, you also add tanks, pressurization, feed systems, valves, and structural reinforcement. Each kilogram of propellant often drags other kilograms with it, and the total mass climbs quickly. Then comes the third edge, which is the one that shifts the tone from engineering optimization to human feasibility. Less payload affects safety and comfort for crewed missions. For robots, payload means fewer instruments, reduced data rate, smaller power margin, or a shorter design life. Painful, but sometimes acceptable if the core objectives remain achievable. For humans, payload is not merely extra capability. Payload is frequently the difference between a survivable mission and an unacceptable risk posture. Payload includes shielding thickness, spare parts, medical capability, redundancy and life support loops, storm shelter volume, water reserves, and the physical space that keeps crew performance from collapsing over long durations. Cutting payload for a crewed vehicle often means cutting into safety margins that you cannot ethically or operationally trade away. This triangle is why so many "why don't we just go faster" conversations end up circling back to propulsion and architecture. If you try to buy speed by adding propellant, the vehicle gets heavier, which demands a bigger rocket or multiple launches. Multiple launches introduce their own risk and complexity: assembly, docking, propellant transfer, and additional failure modes. If you try to buy speed by cutting mass, you quickly collide with hard constraints, especially for humans, where mass is doing essential work: shielding, redundancy, life support. And if you refuse both bigger rockets and reduced safety margins, then time becomes the variable you accept. That's not indecision, it's the triangle doing its job. The triangle also explains why the fast option can be self-defeating for missions that need to stop. A faster arrival typically increases the braking requirement, which demands additional propellant reserved for orbit insertion or complex capture sequences. So the mission pays propellant twice, once to get there quickly, and again to avoid blowing past the destination. That can drive designers towards slower cruise profiles that arrive in a state that's easier to capture, because a slightly longer transit may allow a significantly smaller capture burn, freeing mass for science payload or survivability. For robotic missions, the payload side of the triangle often includes things that directly increase mission resilience: larger antennas for better data return, higher power margin for heaters and instruments, thicker shielding for radiation tolerance, and more robust fault protection. Those benefits compound over time because outer planet missions are long by nature, and reliability is a mission resource. A spacecraft that arrives later, but arrives capable, well-shielded, and with healthy propellant reserves for corrections and science maneuvers, can outperform a spacecraft that arrives fast, fragile, power-limited, and propellant-starved. So the triangle is not merely about minimizing travel time. It is about maximizing total mission value under mass constraints. For humans, the triangle becomes more than a trade. It becomes a constraint that can define mission viability. Comfort sounds optional until you translate it into operational performance. Insufficient volume and inadequate shielding increase stress, disrupt sleep, and degrade decision-making, which increases mission risk. Reducing redundancy sounds like lean design until you remember that deep space offers no rescue and long communication delays slow human-in-the-loop troubleshooting. Cutting consumables sounds efficient until you confront the consequences of a water recovery failure on a multi-year mission. In a crude context, payload is inseparable from risk management, and risk management is inseparable from mass. So the fuel-time-payload triangle is the hidden structure behind every Jupiter timeline claim. If someone proposes a dramatically shorter trip, the triangle forces the follow-up. Where did the extra energy come from? How much propellant did we add? What payload did we sacrifice? What safety margin did we give up? Or what new propulsion technology did we assume? And that last question is the bridge to the next segment, because there are propulsion options that change the shape of the triangle. They don't eliminate the trade-offs, but they move the pressure points. Chemical rockets are the classic option because they deliver high thrust. They can provide a large velocity change quickly, which is ideal for leaving Earth, performing major trajectory corrections, and executing short decisive maneuvers like orbit insertion burns. Their strength is that they can kick the spacecraft onto the desired path in minutes rather than months. That makes chemical propulsion excellent for tight launch windows, high-energy departures, and time-critical events. And it's one reason chemical systems dominate launch vehicles and many deep space mission-critical events. The weakness is efficiency. Chemical propellants are comparatively low in specific impulse relative to electric systems, so getting large total delta V requires carrying a lot of propellant mass. That feeds directly into the fuel-time-payload triangle. Chemical propulsion can help you go faster, but the mass penalty can become severe, especially if you need substantial braking at Jupiter or complex maneuvers after arrival. Electric propulsion, often ion thrusters or Hall effect thrusters, typically powered by solar arrays in the inner solar system, flips that trade. Electric thrusters have very high propellant efficiency, meaning they can achieve large total delta V using a relatively small amount of propellant. The catch is thrust. Electric propulsion produces a gentle push, not a kick. Instead of a short burn, you get long-duration acceleration, hours per day, day after day, for months or years, gradually reshaping your spacecraft's solar orbit. This is why electric propulsion can feel like sailing rather than launching. You don't brute force your way onto a new trajectory, you continuously nudge your path until it becomes what you need. That efficiency can free mass for payload, shielding, and redundancy, or allow missions that would otherwise be impossible with chemical propellant budgets. But the timeline consequence is the one that matters for the script. Electric propulsion often implies long, gradual acceleration, which can translate into longer overall travel times. Not always, but often, because you are trading thrust for efficiency. In many mission designs, the spacecraft spends a long period spiraling outward from the inner solar system to build the required energy to reach Jupiter's distance. Even if the total delta V capability is impressive, the low thrust means you can't instantly reshape your orbit to meet a narrow timing opportunity. You have to plan around long arcs of continuous thrusting and the power available to do it. Solar electric systems also face a practical ceiling as you go farther from the sun. With less sunlight, you get less power, which means less thrust, which slows the rate at which you can keep accelerating. That doesn't make electric propulsion useless beyond the asteroid belt. Missions can mix strategies or use different power sources, but it does mean solar electric tends to be most potent earlier in the journey. A practical way to summarize the difference is this. Electric propulsion buys you time with propellant mass, while electric propulsion buys you propellant savings by spending time. Chemical systems are like taking a sprint, big effort, short duration, while electric systems are like an endurance climb, small effort sustained over long periods. And the mission architect's job is often to hybridize, use chemical propulsion when you need decisive high-thrust events like departure, major targeting, and capture, and use electric propulsion when you want to accumulate large orbital changes efficiently without carrying huge propellant loads. That hybrid thinking can reshape the triangle by moving mass away from chemical fuel and into power generation and thruster systems, which can be advantageous for label-rich robotic missions and potentially for certain cargo-first architectures. This comparison also clarifies why faster is not synonymous with more advanced. Electric propulsion is technologically sophisticated and extremely capable, yet it can still produce a longer cruise if the mission is power limited or if it prioritizes efficiency and payload delivery over minimum time. Conversely, a purely chemical mission can be relatively fast but mass inefficient, forcing painful payload cuts or demanding very large rockets. Each approach is rational depending on what the mission values most: the stopwatch, the payload, the cost, or the overall success probability. And once you start talking about electric propulsion, you immediately run into the bottleneck behind it: power. Solar power fades with distance, and Jupiter is far enough away that long-duration operations often need either very large power systems or an alternative source. That is the natural bridge to the next accelerant people bring up when they want shorter Jupiter timelines without crushing payload: nuclear power and nuclear propulsion concepts, which can keep you powered far from the sun, and in some configurations potentially reduce travel time, at the cost of major engineering, testing, and policy hurdles. Electric propulsion quickly runs into a simple limitation as you push outward: power. Solar arrays that feel generous near Earth produce far less energy in the outer solar system, and while you can scale arrays up, you eventually collide with mass, structure, deployment risk, and low thrust performance that dwindles just when you want it most. That's why nuclear keeps coming up in serious discussions about shortening the clock to Jupiter, not as a single magic engine, but as two related accelerants: nuclear power, to keep spacecraft systems running far from the sun, and nuclear propulsion, to change the propulsion side of the fuel-time-payload triangle in more favorable ways. First, nuclear power in space is about steady, reliable electricity where sunlight is weak or operationally inconvenient. Historically, that includes radioisotope power systems for modest power levels, and it can also include compact fission reactors for higher power. The key timeline impact is indirect, but important. Abundant, stable power supports stronger communications, more capable thermal control, more robust fault protection, and crucially, propulsion options that don't depend on sunlight. NASA has repeatedly framed small fission systems as enabling long-duration surface and deep space operations, including work like the kilopower effort and follow-on fission surface power concepts. In a Jupiter context, nuclear power can reduce design compromises. You're less constrained by sunlight availability and can keep instruments, heaters, avionics, and autonomy systems healthy over long cruise and operations phases. Then there's nuclear propulsion, which comes in two headline categories that map neatly onto the thrust versus efficiency trade you've already seen: nuclear thermal propulsion, NTP, and nuclear electric propulsion, NEP. NTP is the high-thrust cousin. Instead of burning chemical propellants to make hot gas, a reactor heats a propellant, often hydrogen, to extremely high temperatures, and that hot propellant expands through a nozzle to make thrust. The value proposition is simple: higher efficiency than chemical while retaining high thrust, which means you can do decisive burns, departures, major maneuvers, without carrying quite as punishing a propellant fraction. NASA and DARPA publicly positioned NTP as an enabling capability for faster human missions, at least in the Mars context, through efforts like the Draco demonstration concept. For Jupiter, the same logic applies in principle. Higher performance, high-thrust propulsion can reduce transit time, expand feasible launch windows, and potentially make arrive and brake less mass-destructive than pure chemical designs. NEP is the efficiency-focused cousin. A reactor generates electricity, and that electricity powers electric thrusters that accelerate ions or plasma to very high exhaust velocities. NASA describes NEP in exactly those terms. Fission heat becomes electricity, which then drives electric propulsion. The timeline angle is nuanced. NEP often remains low thrust, so it doesn't give you the cinematic punch-it-and-go feel of chemical or NTP. It gives you long, continuous acceleration. But unlike solar electric propulsion, NEP doesn't fade as you move away from the sun, which means you can keep thrusting efficiently in the outer solar system instead of coasting for long stretches. In the right architecture, especially cargo-first or pre-deployment missions, NEP can reduce total trip time to distant targets compared with power-starved solar electric options, while still being extraordinarily propellant efficient. So why aren't we already using nuclear systems routinely to chop Jupiter timelines down? Because nuclear is not merely a better engine, it's a bundle of engineering, testing, safety, and policy hurdles that are scheduled drivers in their own right. On the engineering side, NTP demands materials that survive extreme temperatures and hydrogen exposure, reactor control that is stable across many throttle points, and a propellant management problem that's deceptively hard, storing and handling cryogenic hydrogen for long durations without unacceptable boil-off or tank mass penalties. NEP demands high-reliability space reactors, substantial radiation shielding to protect the electronics and crew, and a major thermal management challenge. Waste heat must be rejected, which usually means large radiators that add mass, complexity, and deployment risk. On the policy and programmatic side, launching nuclear material involves layered oversight, safety analysis, environmental review processes, and interagency launch authorization frameworks. In the U.S., launch authorization processes for space nuclear systems have been formalized in policy guidance that lays out tiered review and approval approaches. And analyses of the process emphasize that environmental review and safety review components can be among the longer schedule elements. Even when the technical case is strong, the mission still has to prove that launch and contingency scenarios are acceptably safe, and that proof is documentation-heavy and testing-heavy. Finally, there's the blunt reality that nuclear propulsion is vulnerable to shifting priorities and budgets. NASA and DARPA's 2023 announcement highlighted an ambition to demonstrate NTP as early as 2027, but more recent reporting in 2025 described proposed budget choices and partner decisions that would halt or cancel specific demonstration efforts, an illustration of how long-horizon propulsion development can be disrupted even when the physics case remains compelling. The practical takeaway is that nuclear can be a genuine accelerant for deep space timelines, but it carries a second schedule attached: the time to mature the technology, qualify it, win approval to fly it, and sustain funding. Put all of that together and you get a realistic, high-level conclusion. Nuclear power helps you operate robustly far from the sun, reducing constraints that quietly stretch missions. Nuclear propulsion, especially NTP for high-thrust maneuvers and NEP for efficient long-duration thrust, can, in principle, shorten the clock to Jupiter or make faster trajectories feasible with healthier payload margins. But nuclear doesn't erase trade-offs, it moves them into new domains: reactor development, thermal management, shielding, regulatory approval, and program stability. And that's the bridge to what matters if humans are ever part of the plan. If nuclear changes the propulsion and power picture, how would an actual crew campaign get staged in reality, with cargo pre-deployment, redundant systems, and multiple missions building toward a first arrival? If nuclear power and propulsion are the kinds of accelerants that might make a Jupiter-bound crew vehicle technically plausible, they still don't turn the journey into a single heroic launch followed by a single triumphant arrival. The reason is straightforward. A crewed mission to the Jovian system would not be designed as a one-off flight. It would be designed as a campaign. In other words, the first human arrival would almost certainly be the visible milestone of a multi-mission timeline that quietly did most of the hard work beforehand, moving mass, reducing risk, and building an operational safety net that a single spacecraft could never carry on its own. The first layer of that campaign is pre-deployment cargo, and it would be non-negotiable for any credible architecture. Cargo missions can tolerate longer travel times and higher risk than crew, and they can be optimized for mass delivery rather than habitability. Long before the crew departs, you would likely send spare parts, consumables, radiation shielding mass, often water or other multifunction mass, communications relays, navigation beacons, and power systems. If the plan involves operating near a moon, cargo could also include surface elements, power units, science stations, landing aids, and shelter materials, depending on the destination. This is how you shift the mass burden off the crew vehicle. You don't ask one ship to be everything, you seed the destination with resources and capabilities so the crew arrives into an environment that is already partially prepared. The second layer is infrastructure and staging, because Jupiter is far enough away that direct starts to look like an unnecessary penalty if you can build intermediate capability. A serious campaign would likely include some combination of assembly and checkout in Earth orbit, potential refueling or staging at cislunar space, and possibly the use of depots or modular propulsion stages that can be reused or repositioned. Even if you never build a station in the science fiction sense, you would build an infrastructure workflow. Repeated launches delivering modules, propellant, and spares, a standardized interface for docking and power and data, and an operational cadence that allows thorough testing before committing humans to the outbound leg. This is where the timeline expands in a way the public rarely sees, not because engineers are slow, but because the only rational approach is to convert an expedition into a sequence of smaller, testable steps. The third layer is redundant vehicles and rescue logic, because Jupiter distances make rescue look different than it does in low Earth orbit. You cannot count on a fast external rescue, so redundancy has to be baked into the campaign. That can mean multiple transport elements, for example, a primary habitat and propulsion stack and a secondary lifeboat-style return capability, duplicated critical subsystems, and mission rules that avoid single-point failure pathways. It can also mean parallel assets, a communications relay that is independent of the crew vehicle, a navigation capability that doesn't rely on a single antenna, and pre-positioned spares that reduce the chance a single failure becomes catastrophic. The timeline implication is that the mission begins years earlier because those redundant assets must already be in place and proven before a crew departure is approved. The fourth layer is staged commitment, because a crewed Jupiter mission would almost certainly be structured with decision gates that allow the program to stop safely before it crosses certain thresholds. In practice, that means you'd see a sequence like in uncrewed technology demos of propulsion and power systems, uncrewed deep space duration tests of life support and thermal control, cargo pre-deployments and system verification at the destination, a final integrated rehearsal with the actual flight hardware, and only then the crew launch. Each stage is designed to reduce uncertainty before you accept the next risk. This staged planning isn't bureaucracy, it's a recognition that at Jupiter, errors are not quickly reversible, and you have to buy down unknowns while you still can. And then there's the often overlooked layer, operations and logistics as a timeline item. A mission campaign needs ground systems, deep space network capacity, continuous flight control staffing, medical support planning, autonomy validation, and contingency procedures that are far more demanding than most robotic missions. It also needs a supply chain capable of producing and qualifying spares for years, because you don't merely build a spacecraft, you sustain a mission system across a long arc of time. That operational reality typically pushes you towards a model where multiple missions share common components and interfaces, because standardization is how you make a multi-mission campaign survivable to budgets and schedules. So when someone asks how long would it take humans to go to Jupiter, the honest answer is that the transit time is only one slice of the timeline. The more realistic picture is cargo goes first. Infrastructure and redundancy are established, systems are tested in escalating environments, and only then does the crew vehicle depart. Because the first human arrival is not a single trip, it is the final step in a deliberately layered campaign designed to make deep space travel something closer to an engineered operation than a gamble. And once you accept that campaign framing, the next constraint becomes personal rather than mechanical. Even if the hardware can run for years, can the human body and mind tolerate the duration in the environment? And how do those health limits push planners toward faster transits if technology can deliver them? That campaign-style timeline sounds methodical on paper. Cargo first, redundancy first, staged commitment, until you add the constraint that cannot be debugged with spare parts, the human body. For crewed deep space travel, the limiting factor is often not whether the vehicle can survive the calendar, but whether the crew can remain healthy and operational across that calendar. And that's where long-duration health constraints become a quiet but decisive driver of how long to Jupiter, because they add pressure in one direction, shorten transit time whenever technology can do so without collapsing safety margins elsewhere. The first constraint is microgravity, which is less about discomfort and more about progressive physiological change. In prolonged weightlessness, the body adapts in ways that are convenient for floating but costly for performance. Muscle mass and strength decline without aggressive exercise countermeasures. Bone mineral density decreases. Cardiovascular conditioning changes because the heart and blood vessels no longer work against gravity. Fluid shifts toward the head can contribute to vision-related issues, and sensory motor systems recalibrate, affecting balance and coordination when gravity returns. A well-designed exercise program can mitigate portions of this, but it does not make microgravity a non-issue, especially over multi-year durations. The longer the transit, the larger the operational burden. More time devoted to exercise, more wear on exercise hardware, more risk of injury, and more reliance on medical autonomy far from Earth. That reality creates an obvious planning instinct. If you can reduce transit time, you reduce the cumulative microgravity tax on the crew. The second constraint is isolation and confinement, which becomes more than a psychological footnote when the mission duration stretches into years. A crewed Jupiter mission would involve prolonged separation from Earth, limited real-time contact with friends and family, a small social group with no ability to rotate out, and a living environment where privacy is scarce and monotony is structural. Add to that the operational demands of deep space travel, maintenance, alarms, procedural workloads, and you get a performance risk as much as a well-being risk. Over long durations, fatigue, interpersonal friction, sleep disruption, and cognitive load can become mission-affecting, not merely unpleasant. The calendar matters here because resilience is not infinite. A crew can adapt and perform exceptionally well, but the probability of compounding stressors rises with time, and the mission must be robust to human variability, not just human best-case behavior. Shorter transits reduce that cumulative exposure to confinement stress and lower the duration over which the mission must maintain peak team functioning. The third constraint is the hardest to negotiate with operations: radiation exposure during transit, plus the additional radiation hazard in and around the Jovian system. Even if you choose trajectories and operational zones that minimize time in the worst regions near Jupiter, deep space itself is not benign, and a long cruise means a long interval accumulating dose from galactic cosmic rays and sporadic solar particle events. Radiation drives design choices, shielding, storm shelters, mission timing, but it also drives time choices, because exposure is to first order cumulative. If a crew spends fewer months in transit, they generally receive less integrated dose during that phase, all else equal. That makes faster is safer an intuitive headline, until you remember the triangle. Faster often requires more propulsion capability, which can demand mass you might otherwise allocate to shielding and redundancy. So planners are pulled into a balancing act. Reduce time to reduce dose, but do not reduce shielding to buy that time, or you may negate the benefit. Put together, microgravity, isolation, and radiation create a set of practical limits that do not show up in robotic missions. Robots don't get osteoporosis. Robots don't lose sleep. Robots don't experience mission-degrading stress. That difference is why crewed missions tend to value shorter transits more strongly than robotic missions do, even though crewed missions are also heavier and therefore harder to accelerate. It's not that mission designers are impatient, it's that human health turns duration into a risk multiplier. Every extra month is more exposure, more maintenance cycles, more opportunities for small problems to become big ones, and more time the crew must perform at a high level, while far from rescue and far from real-time support. This is why discussions about enabling humans to the outer planets so quickly converge on technologies and architectures that can shorten the transit without hollowing out safety. Higher performance propulsion, in-space staging and refueling, artificial gravity concepts, even partial gravity through rotation, improved radiation forecasting and shielding strategies, and life support systems that can run longer with fewer failure modes and less crew time. If those capabilities exist, they push the design point toward faster transits because the health benefits are tangible. If they don't exist, you can still design a mission, but you must accept that the crew health management system becomes a primary payload. Exercise infrastructure, medical equipment, psychological support tools, and extensive redundancy in the systems that keep the habitat livable. So long-duration health constraints don't just add some extra considerations, they reshape the definition of what a plausible human Jupiter timeline looks like. They introduce a strong incentive to minimize time spent in transit, but only to the extent that you can do so without trading away shielding, redundancy, and abort robustness. Which brings the narrative to the point where a single number is no longer credible. The honest answer has to be scenario-based, because robotic typical, robotic fast, and human plausible are not variations of the same problem. They are different optimization targets with different risk tolerances and different limits. So what's the honest answer to how long would it really take us to go to Jupiter? It's not one number, because the number is not a property of Jupiter, it's a property of the scenario you choose. Once you account for moving planet geometry, non-straight line trajectories, launch windows, gravity assists, braking, radiation, communications lag, and for humans, life support and health limits, the question becomes which mission class are we talking about and what is the mission trying to do at arrival? With that in mind, here are 3 quick scenarios that map to the way real mission planners think. In a robotic typical scenario, the common, cost-effective approach used for many serious science campaigns, expect the travel time on the order of several years, often roughly 5 to 8 years, depending on the exact launch opportunity, gravity assist strategy, and whether the mission must arrive in a way that supports orbit insertion and long-term operations. This is the optimized for payload and reliability profile. You accept a longer cruise because it keeps departure energy reasonable, preserves mass for instruments and shielding, and can reduce how punishing arrival and capture have to be. It also fits within the realities of launch vehicle performance and program budgets. If you can deliver a robust spacecraft that survives Jupiter's environments and returns large volumes of data for years, the scientific payoff usually dominates the cost of waiting longer to get there. In a robotic fast scenario, we want to get there quickly and we accept trade-offs, think roughly 1.5 to 3 years as a plausible ballpark for getting to a robotic spacecraft to Jupiter's vicinity if you are willing to pay for higher departure energy and often accept a flyby style arrival or a more demanding capture plan. This is where the triangle shows its teeth. Going faster typically requires more launch performance, lighter payload, and tighter margins, and it often means arriving with higher speed that makes staying harder. Fast robotic missions are most naturally compatible with flybys or limited campaigns, where the mission goal is reconnaissance, broad measurements, or a brief high-value encounter rather than deep, sustained operations. In principle, you can pursue faster arrivals, but in practice, you spend a lot of mass, cost, and risk budget to do it, and the mission definition has to match that reality. In a human plausible scenario, the we're trying to keep people alive, healthy, and operational profile, the travel time is constrained in both directions. On one hand, the same mass and propulsion realities that make crewed vehicles heavy can push you toward longer transits if you rely on conventional propulsion and conservative architectures. On the other hand, microgravity, isolation, and radiation exposure push you toward shorter transits to reduce cumulative health and dose burdens. The result is not a neat single number, but a tension. With near-term conventional assumptions, a crewed Jupiter mission would likely be a multi-year undertaking that is only credible as a broader campaign with pre-deployed cargo and extensive redundancy. With more advanced propulsion and power and mature operational infrastructure, you could aim for shorter transits, but that requires capabilities that are not routine today at the scale and reliability human missions demand. Human plausible is therefore less a stopwatch estimate and more a technology and architecture statement. The timeline you can justify depends on what propulsion, shielding strategy, abort posture, and campaign infrastructure you can actually field. The key takeaway from these scenarios is that the travel time to Jupiter is not a trivia fact. It's an output of design choices. When someone insists on one definitive number, they are usually unknowingly locking in assumptions about propulsion, payload mass, arrival objectives, and risk tolerance. The honest answer is scenario-based. Robotic typical is measured in several years because it maximizes payload and robustness. Robotic fast can be shorter, but usually at the expense of payload and staying power. And human plausible is constrained by health and safety in a way that makes the problem fundamentally different from robotic travel time math. And with those scenarios on the table, the story is ready for its final closure. If the distance varies, trajectories aren't straight lines, gravity assists can lengthen trips, and human safety drives the hardest constraints, what is the memorable bottom line, and what breakthroughs would actually shorten the clock the most? So here's the memorable takeaway that cuts through all the numbers. Jupiter isn't a fixed mileage destination. It's a moving target. The path to reach it is rarely a straight line, and the fastest looking routes often aren't the smartest once you account for fuel, braking, radiation, and what arrival is supposed to mean. Earth and Jupiter slide around the Sun on their own schedules, so the baseline distance expands and contracts with alignment. The spacecraft doesn't aim at Jupiter and go. It reshapes its orbit around the Sun and coasts along a gravity-shaped arc, which is why launch timing and geometry can matter almost as much as raw rocket power. And the famous cheat code, gravity assists, can absolutely make missions possible by borrowing momentum from planets, but it often does so by trading a shorter route for a longer itinerary, adding months or years because you're waiting for the solar system's choreography to line up. Then there's the part that makes the human version of the question fundamentally different. Human safety is the hardest constraint, not distance. Robots can afford to wait. Humans carry a clock inside their biology. Microgravity deconditions the body. Isolation erodes performance, and radiation accumulates whether the crew is ready for it or not. Meanwhile, Jupiter's own radiation environment punishes time spent in the wrong regions, reshaping approach corridors and orbit choices even for robots, and turning hang out near the planet into an exposure management problem. Communications lag ensures you can't operate by reflex. You need autonomy and careful pre-planning. And the braking problem means you don't just get there. You must shed enormous energy to stay, which is why so many missions accept flybys or multi-step capture strategies rather than paying for a single massive propellant-hungry stop at arrival. If you want the one sentence that matters, it's this. The trip time to Jupiter is the output of a trade. Time versus energy versus mass, and humans force that trade to be made under stricter safety rules. That's why the same destination yields answers ranging from a couple years to many years, and why no honest answer can ignore mission type, arrival goal, and propulsion. And if you want to know what breakthroughs would shorten the clock the most, they're not cosmetic upgrades. They're the capabilities that change the triangle itself. Higher performance propulsion that delivers large delta V without a crushing propellant mass penalty is the biggest lever. Whether that's mature nuclear thermal concepts, high-power nuclear electric systems that can keep thrusting efficiently far from the sun, or other advanced propulsion approaches that combine meaningful thrust with better efficiency than chemical. Close behind that is radiation mitigation that's more effective per kilogram, better materials, better storm shelter integration, and mission architectures that use consumables and structure as shielding without ballooning mass. Add in-space refueling and staging so you're not forced to launch the entire mission as one monolithic stack, and you unlock faster trajectories without gutting payload or safety margins. Finally, improved autonomy and reliability matter because at Jupiter distances, the ability to operate safely with less ground intervention and fewer failures is what turns ambitious timelines from possible in theory into credible in practice. So if you remember nothing else, remember this. Jupiter travel time is not one number. It's a choice of route, a choice of arrival, and the choice of what you're willing to spend. Fuel, payload, complexity, risk, or years. The fastest trips will come from propulsion and infrastructure breakthroughs that let us buy speed without sacrificing the mass that keeps missions, especially human missions, alive long enough to matter. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.